Hi, today I'll be presenting Lab 1, Constant Velocity. The problem we're attempting to solve in this lab is to predict motion at a constant velocity. Theoretically, if we know the force at play, we should be able to predict the motion of an object. Newton's first law of motion states that an object in motion will stay in motion unless acted upon by an unbalanced external force. And Newton's second law of motion tells us that acceleration equals the net force divided by the mass. And by this, if the net force is zero, the acceleration on an object is also zero. The experimental setup that I use for my lab is a ball of 0.033 meters rolled across a desk. I mounted the camera above the desk under the bed in a stationary position. I use a program tracker to analyze the motion of the object. I use GlowScript to model and predict the motion of the ball. I use Google Sheets to make the graphs that will be shown throughout the presentation. I made some assumptions while doing my lab. The table is level, the camera lens is not distorted, the sum of the net forces after the ball is released is of the vector of 0, 0, 0 newtons. The friction in the lab is negligible. The air resistance on the ball is also negligible, and the ball moves at a constant velocity throughout the entire experiment. In my tracker model, I started at frame 11 and ended at frame 41. With 30 total frames analyzed at a frame delta t of 0.033 seconds, I analyzed 1 second of the ball's motion. I calibrated the tracker with the ball's diameter of 0.033 meters, and I centered the axis at the ball's starting point, with the positive x going right. A few formulas I used in this lab was v equals delta r over delta t. I used this to calculate the velocities throughout the lab, dividing the change in distance over the change in time. I used another formula to show constant motion as Vf equals Vi plus F net divided by mass times delta t, and when the net force is zero, the final velocity equals the initial velocity. And then I use a position update formula in my tracker to predict the motion, and that is Rf equals Ri plus V average delta t. Seen at the bottom of the slide are the equations I used and the work I did to calculate the initial velocity, the average velocity, and the final velocity. For the initial velocity, I used the first and second point. For the average velocity, I used the first and last point, and for the final velocity, I used the last 2 points. Here's a video of my tracker recording. Here's my GlowScript code. I started the ball's initial position vector at 0.000500, which was its initial position. I use a variety of different velocities, including the initial velocity, the average velocity, and the final velocity, to create 3 different models, which can be shown in the next few slides. The time started at 0, and I used a delta t of 1 over 30 as the delta t tracker was 0.033 seconds. I used the position update formula and the velocity update formula to update the velocities and accurately predict the motion. Here's a recording of the GlowScript. As I said before, I used 3 models: the V initial model, the V average model, and the V final model. These used velocities calculated between the first 2, first and last points. On the slide here are the calculated velocities. For the V initial model, it was a slight underprediction of the actual time. The V average model, as it used V average, was perfectly on the line. And using V final, I got a slight overprediction. What if the axes were flipped? The current positive x direction is to the right, but if it was flipped, it would be to the left. The ball would have the same distance traveled, but would have negative displacement. Instead of 0.5110 meters in the x direction, it would be negative 0.5110 meters. The slope of the distance versus time graphs would also be negative. The graphs would also be flipped, with x getting further negative instead of positive. What does it mean? When looking at the forces, we assumed that the net force on the ball was 0. As the models were able to accurately predict the motion of the ball, we can see that this was true. It is not possible for us to say how many pushes or pulls were acting on the ball, as we do not know how many forces. Error sources and how to improve. There was friction, which we can't really account for, but we have to assume is negligible. The table was a little uneven, and next time I can make sure the table is level. The surface was also not perfectly smooth, and this can be remedied with a smoother surface. The object didn't also travel exclusively in the positive x direction, with a little wavering in the y direction. This can be corrected if the object travels in a straight line. There's also slight camera distortion, which we can be aware of but can't really correct. To conclude, if we know the net force or lack of net force is acting on an object, we can predict its motion. We can use Newton's first and second laws of motion to do so. This includes the first law of inertia and the second law stating that the net force equals mass times acceleration. Using these, we can form accurate models to predict motion. Thank you.